So we've got two reactions of the same substrate here. We got a benzene ring, methyl and a bromine. First thing you should do is draw in the hydrogens on those two chiral centers. And we could actually name it and determine those two stereocenters. So we've got a stereocenter here and a stereocenter there. It's a benzene derivative. It's got a substituent on there. And if this is carbon 1, then it's a 3-carbon substituent. So there's a 1-methyl and a 2-bromo. If you look at the chiral center, this carbon is the most important that's attached to there because this carbon is attached to bromine. The benzene ring is number 2 because it's attached 3 times to carbon. Methyl is number 3, so if you're in the back of the molecule looking out, you'll discover that that's an S stereocenter. Bromine is the most important. This carbon's bound to multiple other things, so that's 2, 3, so this is an R stereocenter, so it's 1s and 2r. And then it's 2-bromo, 1-methyl propyl benzene. We've got two different sets of reaction conditions, and the first thing to do is decide which one of these is going to be the E1 elimination, which one's going to be the E2 elimination. That's kind of the key piece on that one. Since there's one equivalent, that's fairly low concentration. So that's going to be the E1 pathway. And then the key here is to recognize that as LDA, which is lithium diisopropylamide. And lithium diisopropylamide is one of the strong hindered bases, which means that's an E2 elimination. And it also means that the Hofmann product is going to be the major product. All right, strong hindered bases will take the most accessible hydrogen. So that tells us what the pathway is going to be. So for the first one, right, for the E1 reaction, we know that the rate, which we define as the disappearance of the substrate with respect to time, is just equal to K times the substrate. And we know that for E2, the rate law is the same disappearance of substrate. But now it depends not only on the substrate concentration, but also on the base concentration, which in this case is the LDA. It's this CH3 2CH twice N minus. That's the diisopropylamide ion, which actually looks like this if you draw it out. It's got two isopropyl groups attached to benzene. I didn't mean to write that next to the E1 rate law, right? That's not part of the E1 rate law. So bimolecular here, bimolecular rate determining step, concerted reaction, unimolecular here, and the carbocation intermediate with the E1, same as for E2. Right. Stereochemically, the E2 reaction requires the anti-periplanar arrangement of the hydrogen that's removed and the leaving group. E1 doesn't have any stereochemical requirements. Right? Regiochemically, E1 is going to always yield the most stable alkene, which is the more substituted alkene, and the E2 elimination is going to yield either the most substituted alkene or the less substituted alkene, depending on the steric hindrance of the base. This one happens to be a strong hindered base, which means we're going to get mostly the less substituted alkene. So we can think about the products. Right? There are adjacent hydrogens on carbon 1 and adjacent hydrogens on carbon 3, and because there's a possibility of E and Z isomers in the alkene, even for the more substituted one, right, there are two possible products. So we can get the double bond that looks like that, or we can get the double bond that looks like this. Right? Those are stereoisomers. One of these is E and one of these is Z. And we could also take off the hydrogen on the other carbon and end up with the one substitute, in which case this chiral center remains intact. So if it's E1, right, this is the trace product. We're not going to see very much of those. Which of these two would you think would be the major product? The one on the left or the one on the right?
The right.
Why?
It's trans.
There is no cis and trans here, right? Because if you say it's trans, do you mean it's trans like to this methyl group, or do you mean it's trans to the phenyl group? We would actually have to.
The methyl group.
We'll actually have to use the E and Z isomer if we want to specify. Right? So in this case, the most important substituent on this carbon is the benzene ring, and the most important substituent on this carbon is the methyl. Methyl beats hydrogen, benzene beats methyl. So this is actually the E isomer. And this one, because the most important substituent on each one is on the same side, this is the Z isomer. Zusammen means the most important ones are on the same side, and gegen means the most important ones are on opposite sides. So you can't say cis or trans without specifying what you're cis or trans to, and that's why we use the different nomenclature. So is the E isomer or the Z isomer going to have larger steric hindrance? That's the key. Because whichever one has the more steric hindrance, that's the one that's going to be the minor product. And maybe if I draw this hydrogen in, that will help you decide. Which one looks like it's going to have the biggest steric collisions?
See?
This one, right? The methyl group isn't going to really want to talk to that hydrogen. These two hydrogens are less of a problem. So the major isomer should be this E isomer where the bulkiest substituents are on opposite sides. The minor product should be this Z isomer and then just traces of that for E1. For E2, with the sterically hindered base, right, the strong hindered base, we would expect this one to be the major product. And actually, we can't get both of these. Only one of these is possible because of the requirement for the anti-periplanar, which we'll see in a second. So for the E1, I don't really need to worry about stereochemistry. Right. But for the E2, I'm going to need to rotate the molecule in such a way that we get the leaving group into the plane of the page. So for E1, I'm fine just starting here. The bromine has to leave to form a carbocation intermediate. That first step in either SN1 or E1 is always in equilibrium. So we're going to form a planar carbocation here. And then in the second step, the base, which is hydroxide ion, is going to come in and pluck off the hydrogen and generate the pi bond. And I'm showing that one, right? The methyl groups are on the same side once that hydrogen comes off. So as I'm showing that mechanism, I would be generating the E isomer, which is in fact the major product, which was my intent, right? But you could also show this rotating around. So if you rotated this 180 degrees, right, you could get the hydrogen on the other side. So we'd have the methyl group down here and the hydrogen up there. And then when we remove that hydrogen, we would get the Z isomer. Since there's free rotation about that single bond, both of these are possible. So there's the E, which is the major. Here's the Z, which is the minor. And I won't show the, well, maybe I will. I'll show the trace as well. Why not? I didn't actually require you to do that, but so for the trace product, if you wanted to show it, we would actually need to show the hydrogens on this methyl group. So we would draw those out. Got the positive charge here, and now the base would take one of these hydrogens off instead. Doesn't matter which, they're all equivalent. And that would generate the trace product, where the stereocenter stays intact, and we generate a monosubstituted alkene. So that's the E1 mechanism. The energy diagram for E1, there's two steps. The first step is going to be endothermic because it generates the carbocation, and then the second step, the removal of proton, will be significantly exothermic. Right, so this is loss of leaving group, and then this is removal of proton. Classic double-humped energy diagram that you're going to see for either an E1 or an SN1 reaction. So now let's talk about E2. The E2 pathway is a little bit more complicated because we have to have that anti-periplanar arrangement. And right now the bromine's not in the plane of the page, which means I need to rotate it until it is. And you might find that it's easiest to figure out your rotation if you redraw that as a Newman projection. Usually it's best to put the carbon that has the hydrogen on it in the front. So if I were to do that, the benzene ring is down here. Okay, this is the CH3 group, and then my CH3 group on the front carbon would be over here, and my bromine is on the same side as the hydrogen. So you'll see that we don't have a hydrogen here, right, which means we can't do an elimination pathway. What we're going to have to do is we're going to have to rotate it so that this hydrogen is over there, and the bromine is kind of in the plane of the page. Probably the easiest way to rotate it from this structure is to leave this guy alone for now. Spin it so the bromine is over here where the methyl is. And if the bromine goes where the methyl is, the methyl goes where the hydrogen is, and the hydrogen goes where the bromine used to be. Right. So that puts the bromine where it needs to be. Now I need to spin that to put the hydrogen over there. So I need to redraw that. The hydrogen is going to be, the hydrogen is going to be sticking out. Now the hydrogen is the anti-arrangement, and if I remove that, the phenyl ring goes back. And I could actually just write it as C6H5 if I want to. And the methyl group's up here. So now I'm situated so I can actually show the E2 elimination. So I've got this nitrogen anion that is going to pluck that hydrogen off, form the pi bond, and remove the bromine all in one step. This is a non-reversible reaction, so in the transition state I'm going to want to show the partial bond to the hydrogen. Delta minus on the nitrogen now. I'm going to show the partial bond to the carbon. My phenyl ring, which I could also write as pH if I wanted to, is back. I've got a partial pi bond forming, and I'm breaking the bond to the leaving group and starting to put a negative charge on it. So it looks like that. You'll notice that the methyl groups are opposite each other. One methyl's on the front, so the phenyl and the methyl are going to end up on the same side, and my product is going to look like this. So there's the benzene ring, methyl over here, so hydrogen over there, the methyl group back. So this is the minor product, and from the E2 we can only get this isomer, right? The Z isomer, which is the less stable. We can't get this one, so there's none of that. There's just two products. The major product is this less substituted alkene. The minor product is this one here. And if I want to show that one, I need a different kind of orientation of the molecule, because I need to make this methyl group and that bromine be in the same plane. So I got my hydrogen here, I got my bromine sticking out, my hydrogen back, and my CH3. In this case, what I want to do is leave the methyl group alone, right? So that the methyl group is kind of where it needs to be, but I need this bromine to be here. So I need to redraw that molecule so that the methyl group is here. So I have my hydrogens on my methyl group. I need to put the bromine here, right, so that it's opposite, so I have that anti-periplanar. Arrangement. So I'm going to kind of spin this down, put that bromine there, which will bring this whole group here, which I'm going to write as R, just so I don't have to keep drawing it. That's going to go here, and then this hydrogen will go there. And that should give me still the R stereocenter, right? Bromine is number 1, this large R group is number 2, this is number 3, right? You can see that with the hydrogen back, we're still going clockwise, right? So I've still got the right stereocenter at position 2. My nitrogen is going to pluck that hydrogen off, form the pi bond, and kick the bromine out, yielding a transition state that looks like this. There's a partial bond to the bromine, a partial pi bond, a partial bond to that hydrogen, and a partial bond to the nitrogen, and now the charges are split. Right, there's a delta minus on the nitrogen and a delta minus there. And I got 2 hydrogens here, so there's my transition state. And then my product is this R group, the hydrogen. Got my double bond and 2 hydrogens out there, it looks like that. So that's my major product. Energy diagram. Single step, concerted. Just one transition state, one elementary step, and that's what leads to the second order kinetics.